Hi everyone, I'm Julia, the chemistry tutor, and today I am going to talk about gas laws. Well, I'm going to talk about the ideal gas law. There are other gas laws, individual gas laws, and a combined gas law that I will talk about in another video. This video is going to be about the ideal gas law and all of the things that we can do with the ideal gas law. So let's get started. Okay, the ideal gas law is PV equals nRT. And P is your pressure. Okay, and we have several pressure units. I will come back to those in a minute. V is your volume. And that is always going to be in liters for gas laws, because we don't look at gases in terms of milliliters. That's just too little of gas. So like when you buy propane for your grill at home, you buy it in at least a liter, if not 5 liters. Okay, so we measure gases by the liter. Our N is our number of moles of gas. Okay, you might be given information about a solid, okay, and you'll have to convert that over to moles of gas because gas laws are only good for gases. R is your gas constant. I'll talk about that in just a second. And T is your temperature. And that is in units of, here, I'm going to change my color. That's in units of K, Kelvin. Okay, so we have to be in Kelvin. Oh, sorry, that's not Kelvin. That's liters. Okay, so we have to be in Kelvin for temperature, liters for volume, moles of your gas for N, and pressure is going to be in units of, we're typically going to use ATM, which is atmospheres. It's just the pressure of the air in the atmosphere around you. We could use millimeters of mercury or torr. Those are the same thing. Okay, when we're using millimeters of mercury, we're talking about a barometer, okay, that has a tube closed on one end, open to the other end. It's got a little ruler over here, and that's in milliliters. And there's mercury in the tube. Okay, so when the air pressure outside, the atmospheric air pressure gets higher, it pushes down on that mercury, and the mercury in the tube rises, and you get a higher milliliters. Okay, so that's just your millimeters of mercury. Is if you're looking at a barometer, you're looking at how many millimeters is the mercury on that little ruler. Okay, and that's related to the atmospheric pressure outside. Okay, so our pressure units of millimeters of mercury and torr, those are the same thing. Okay, and our conversion for those, I'm going to erase that to give myself some space. Okay, the conversion for these, because we're usually going to be in ATM atmospheres, is 1 atmosphere is 760 millimeters of mercury, which means 1 atmosphere is also 760 torr. Okay, there's another unit you might use, which is PSI, pounds per square inch. If that's what you're filling your tires in your car, that measurement of pressure unit is PSI, pounds per square inch. And the conversion for that is that there is 14.7. Oh, I'm going to write it the same way I was writing it here. That 1 ATM is 14.7 PSI. Okay, so those are your units for pressure. So pressure, we're typically going to be in ATM. You'll have to convert to ATM if you're not in ATM. Liters, moles of gas, and K. So now let's talk about that gas constant. Okay, the gas constant is a constant number. It is always this number, 0.08206 ATM liters over K mole. Okay, those are its units. Those are what it is. And I'm not going to talk about where the gas law comes from, the gas constant comes from. That gas constant comes from relationships of like electricity and energy. And if you want to know where R comes from, talk to a physics instructor, because I'm sure a physics instructor could explain it to you. Your chemistry instructor may be able to. I'm not going to go into it. Just recognize that that is the value for R, and you will need to memorize that most likely. Some instructors use the unit of 8 millimeters of mercury, and if they use that, it's 62.36 millimeters of mercury. Liters is the same, K is the same, mole is the same. The only difference in these two is if you're using ATM or millimeters of mercury, you're using a different number. Now, I can tell you, I've never used the millimeters of mercury number. I actually had to look it up, and I just Googled, conversions to ATM, and I searched forever and could not find a chart that has the R value in millimeters of mercury. So I specifically had to ask, what is the value for R, the gas constant, in millimeters of mercury? And I found one page that told me. So this is not a commonly used unit. It's not used very often. So if I were you, I would not memorize that unless your instructor is using millimeters of mercury a lot. Then that saves you from doing some converting. Okay, but generally we're going to be using this R value. Okay, and so we can know like 4 of those things and solve for the 5th thing, or I could know other things and solve for another thing. Okay, so you can know anything in that equation, 4 things, and solve for the other thing. And R you always know, that's always a given. Okay, so that is what the gas law is, the ideal gas law, PV equals nRT, and that's our units for all of those measurements. There, in the next video that I'm going to do on gas laws, there are other gas laws that are like pressure 1 and volume 1. It's going to be equal to my second pressure and my second volume, or pressure 1, temperature 1 equal to pressure 2, temperature 2. Okay, those are individual laws. And we do combined laws from those. But you notice on this, there's 2 of each thing. Okay. When we're using the ideal gas law, there's only 1 of anything. There's not 2 of anything. So that's how you'll know when you get gas law problems. If I've only been given 1 piece of information, 1 of each thing, 1 pressure, 1 volume, 1 temperature, then I absolutely know I'm using the ideal gas law and not one of these laws here. Okay, because you're going to hear me reference that a lot during this video. Now I'm going to look at a variety of things we can do with the ideal gas law. In most of my videos, I usually do several examples of each type of problem, but there's like 8 different things that we can do. So I'm only going to do 1 example of each type of problem. So if you don't catch it and you need more help, always feel free to email me at, let me get some mark here, at Julia Kim Tutor at outlook.com and set up a private session with me. I would be happy to help you out on doing some more problems of these, okay? All right, so number 1, if I have 4 moles of gas at a pressure of, so I've got my moles, I've got a pressure, and I've got a volume, and they're asking about the temperature. So I've only been given 1 of anything. There's not 2 pressures, 2 volumes, 2 temperatures, 2 values for moles. So we know we're using PV equals nRT. So the way I do gas laws is I'm very organized about it. In case we have to do any kind of converting, I do that over on the side of my paper. And we know R is 0.08206 ATM liters over K in mole. And by the way, some of your instructors might cut that to 3 sig figs and call that 2.1. I'm always going to use the 206. I always go with more sig figs because some instructors use more, some use less. So I always go with the more. Okay, so given our information, our pressure we were given is 5.6 ATM. And I didn't really talk about this specifically why. Remember I said our pressure has to be an ATM, and that is because our R value is an ATM. Our volume has to be in liters because our R is in liters. Our temperature has to be in K because our R is in K. We have to be in moles because mole is in K. I mean, because R is in moles. Okay, but the K value, there's a little more with K. You always have to be in K no matter what for gas laws, because if I had a negative temperature, I would get a negative volume, and that is not possible. So by adding the 273, we always get a positive temperature. Oh, that's not right. Might as well put a number there. So that's 248K. So you always have to be in K, so you never wind up with negative numbers in gas laws. So it always has to be in K no matter what. And when you're using R, you have to be in the ATM, liters, moles, and always in K no matter what. Okay, so we're in ATM, so we don't have to convert that. Our volume they gave us was the 12 liters, and we're in liters, so we don't have to convert that. They told us our moles is 4 moles. So we don't need to do any converting there. And they're asking us about the temperature. Okay, so we don't have to convert everything. So we are isolating T, which means we're going to divide by the NR, divide by the NR, because then those cancel. Okay, I know some students are not really good with algebra, so the way I look at it is I'm isolating my temperature. So I'm going to move everything away from it to its diagonal across the equal sign. It was on the top over here. I'm going to move it to the bottom over here. If it were on the bottom, I would move it to the top on the other side. Okay, so some students really struggle with that algebra rearranging. So move it to its diagonal across the equal sign away from what you're solving for, what you're trying to isolate. Okay, so we have that our T is equal to PV over NR. So now that I have all of my information on the side over here, I can say that my T is equal to my 5.6 ATM times my 12 liters divided by my 0.08206 ATM liters over K mole and my 4 moles. Okay, and I put my R first. Remember, R times N is the same as N times R. It doesn't matter what order they go in over here, as long as they're both in there. Okay, so if we look, we see our ATMs cancel, our liters cancel. And remember, when we're dividing by a fraction, it flips the fraction so that K and mole actually become top units there. So my moles cancel and I'm left with K, which is what I'm looking for. I'm looking for that temperature unit. Okay, so if I do all of that math, and I've already done the math here, so I don't spend all my time on that, I get 204.728 K. And we are at, for our sig figs, we're at 2 sig figs for the 5.6, 1 sig fig for the 4, and 2 sig figs for the 12. So we're going to go with the 1 sig fig. Okay, but 2 does not mean the same thing as 204, so I have to put my zeros in there to get me into the hundreds place. Do not put a decimal on that. A decimal makes that 3 sig figs. Remember, a decimal in the number, your ending zeros are significant. So we don't put a decimal on that, or you could go to scientific notation. Okay. But that looks weird. Like I can't even visualize what that temperature looks like. It's 200K is our answer for this. That's our temperature. Okay, so you see what we do is we just say, I've been given 1 pressure, 1 temperature, 1 mole. They're asking or asked about 1 temperature, 1 volume, not 2 of anything. I'm using PV equals nRT. I write all that on the side. I know what my R is already. Track my information, plug it into my equation, rearrange my equation and plug it in. That is the ideal gas law. Okay, so now looking at number 2, I have a gas held at a temperature. So I have my temperature, I have a volume, I have a pressure, and they're asking me for how many moles. Okay, I haven't been given 2 of anything, 2 pressures, 2 temperatures, 2 volumes, 2 moles. So I'm using PV equals nRT. Okay, my pressure was the 425,600 millimeters of mercury, but we have to be in ATM because our R value is in ATM. So that conversion is the 1 ATM to the 760 millimeters of mercury. Okay, and if we do that, I get 560 ATM. And this number right here was 4 sig figs. So I need 4 sig figs in that number. So I'm going to put a 0.0. Okay, my volume, they told me, was 25,000 milliliters. I need to be in liters because my R is in liters. So I'll write that back over here, 0.08206 ATM liters K mole. Okay, so I have to turn my milliliters into liters. So I have 25, and that's only 2 sig figs because there's no decimal in that number anywhere. So I've got 25 liters. I always do moles last just in case. Okay, so then my temperature was the 922 degrees Celsius. But we have to be in K, so we're going to add the 273.15. And from that, I get 1195.15. This is addition subtraction. So 0 decimal places for sig figs, 2 decimal places. I'm going to go with 0 decimal places. So my temperature is 1195K. Okay. So you might have to do all of the converting. You might need to convert one of them. You might need to convert 2. You might need to convert all of them. Okay, but you just have to make sure you're in those units. This one above was easy. I was given the correct units. I didn't need to convert. This one is a little bit more because I have to do all of that converting first. But now that I've got it, I'm isolating N. So I'm going to move RT to the bottom on the other side. So we know our N equals PV over RT. So my N is equal to my pressure, which was the 560.0 ATM. My volume, which was the 25 liters, divided by R, 0.08206 ATM liters over K mole. And my temperature was the 1195 K. And you see that your ATMs cancel, liters cancel, Ks cancel, moles, which comes to a top unit because it's a fraction on the bottom of a fraction. So I'm left with moles, which is what I'm looking for because that's what they're asking us for, how many moles. So now when I do that math, I got, let me make sure I'm on the right problem here. Oh, there we go. So I got 142.767 and probably some other numbers. Okay, and we're at 4 sig figs here, 2 here, 4 here, 4 here. So I'm going to go with 2 sig figs in my answer. So 14, but 14 does not mean the same thing as 142. So put a 0 on that. Do not put a decimal. That would make it 3 sig figs. So I have 140 moles of my gas. Okay. So those are just general ideal gas law problems where you're given the information in the correct units or you're given the information and you have to convert everything. And before we move to the next problem, let me say sometimes I miscalculate. I double checked my calculations, but sometimes things happen. I'm human. I make mistakes. So if you're calculating along with me and you get a different answer than me and you double check yourself, email me and please let me know so I can correct my video because it happens. I make mistakes. Okay. So now when we're looking at this one, we're asking what is the molar mass. So number 1, we know automatically, I'll write it over here. We want to know how many grams per mole. because that is what molar mass means. Automatically, grams per mole. That's what I want to know. So I've been given a mass of a sample of gas. So they want to know the molar mass of the gas. So we want to know grams of our gas over moles of our gas. Okay. And something to recognize is they just told us our grams of gas. Okay. If we're calculating the molar mass of a gas from this information, then we already know our moles are grams of gas. I'm going to make that a little smaller so I have some space over there. So we want to know grams of gas over moles of gas. And we already know our grams is 5.67 grams. So we know we are not going to use that in our gas law problem. That number's not going to get used. Okay, so I've been given a volume, a temperature, and a pressure. One of everything. I haven't been given two of anything. So P, V, N, T, because we're using PV equals nRT. My pressure they gave us was 1.5 atm, and we're in the correct unit. We need to be in atm. My volume was the 25.6 liters, which we need to be in liters. That is correct. My temperature was the 276 K. We're already in the correct unit. We don't need to convert. N is the only thing we don't know, so we must be solving the gas law for N. Okay, but we already know that because we need to know our moles of gas in order to do our molar mass of the gas. Okay, so when they're asking for molar mass of a gas and they give you the gram, the mass of the gas, you're solving your gas law for moles. But if you don't know what to do on a gas law problem, decide, I've only been given one of anything, I'm going to use the ideal gas law and fill in your information, because then you see there's only one thing you don't know. If there's two things you don't know, we'll get to that in a minute. Okay, but there's only one thing you don't know, so you must be solving your gas law for your number of moles. So if you don't know what to do in a gas law, track your information and solve for the thing you don't know. You'll at least get part of your points. Okay, so on this one, we're solving for N. We're isolating N. So we're going to move RT down to the other side on the bottom, because what we're doing is dividing by RT. So we get that our N is equal to PV over RT. So my N is equal to my pressure times my volume divided by my R, 0.08206 atm liters over K mole. And my temperature was the 276 K. And we see our ATMs cancel, liters cancel, Ks cancel, mole is on the bottom of a fraction. It comes to the top, so we're left with moles. And when we do that calculation, I get 1.6954 moles. And that's my gas, because gas laws are only good for gases. We are technically limited to 2 sig figs on that. So it's those two. But I'm going to go ahead and keep my whole number and put it in up here. And I'll round at the end. I'll round when I'm done. So that's moles of gas. So now if we take our 5.67 grams divided by our 1.6954 moles, we get 3.34420. And we are limited to, on this number, 2 sig figs. Right there. So it's those two numbers. So 3.3 grams per mole. That's my molar mass of my gas. Okay. So that's just something else you can do with a gas law. They give you the mass of the gas and all of the other information. Okay. You don't know what the gas is. So you can't just take your grams and use molar mass to solve for your, because you don't know your molar mass. Okay, that's what we're calculating. So you can do that with the ideal gas law. I'm going to erase a little here so we can see. You can do, let's look at what the next problem is. So what is the molar mass of a gas? If I have the mass of my gas and we're asking for the molar mass of the gas. So again, we want to know how many grams of our gas per mole of gas. Okay, I know that I have, I'm just going to write it up here, the 7.8 grams, just to have that in our head. We have a volume, a temperature, and a pressure. Wow, that degree is really large there. Okay, so I don't have 2 of anything, so I'm using the ideal gas law. PV equals nRT. Pressure, volume, moles, temperature. My pressure is 790 decimal millimeters of mercury. We have to be in ATM. So an ATM, 760 millimeters of mercury. And that is 1.04, 1.039. And I've got 3 sig figs here. And this is an absolute number, so don't use that for sig figs. Okay, so 3 sig figs, so that's 1.04 ATM. My volume, they told us, was 6.7 liters. We don't need to convert that because we're already good. My temperature is 75 no decimal, 75 degrees Celsius. So I have to add the 273.15, and I get 348.15. But addition, subtraction, so 0 decimal places, 0 decimal place, 2, sorry. I'm going to go with 0 decimal places in my answer. So 348K. And some of your instructors might not use the 0.15. You see, it doesn't change the answer. If I had just left off the 0.15, because the 0.15 is not going to round your number up, so it doesn't change your number if you leave it off. Some instructors don't use it, some do, so I always use it. So you see, the one thing we don't know is our moles. So if you didn't know what else to do, you would solve for moles. But that is what we're looking for up here, right? Moles of gas. So we're isolating N. So we're going to move our RT to the bottom on the other side. So my N is equal to PV over RT. So my N is equal to my 1.04 ATM. And you could actually keep that whole number and round at the end. I know some Gen Chem instructors do that, so let's do that. And I'm going to mark above the 3 that that's my sig fig. So I have 1.039, and we put a mark above that. Or under it, you can underline it, whatever your instructor has you do. My volume is 6.7 liters. R is 0.08206 ATM liters over K-mole. And my temperature was the 348K, and we could leave in the 0.15 if you wanted to. And that 8 is my sig fig there. Okay, and so I did not leave those in. I actually rounded before I did this calculation, so you might get a slightly different number than me. Okay, but when I do that, I get 0.2440 moles. And we're limited to 2 sig figs on that one, but I'll go ahead and keep them all. Okay, so to calculate our final calculation, our how many grams per mole, we have 7.8 grams of our gas, and we have 0.2440 moles of our gas. So if you do that calculation, you should get 32 grams per mole. Okay, so write that down here, 32 grams per mole. Okay, so now I have an A to that question. I have a follow-up question to that. Okay, so if this gas were a diatomic molecule, so 2 of the same atom, what is the identity likely to be? Like, what might that gas be? And you might already know off the top of your head if you've been doing a lot of calculations with molar masses. But let's pop over to, I'm going to pop over to, oh, nope, I need that screen. Sorry. So let's go over to the periodic table. Okay, we're looking for something that 2 of them is 32. So if we divide by 2, that means each of them weighs 16 grams per mole. So on your periodic table, what weighs 16 grams per mole? Oxygen, right? So O2 is likely going to be the gas that I have. Okay, so you might need to identify what the gas is, and they'll give you information like that, like, hey, it's a diatomic molecule. Okay, since it's diatomic, we know that we're going to divide that by 2 to get the mass of each one of those atoms in there. Okay, so we can use a gas law to get the molar mass of a gas. I did do 2 of those where you're given your mass of your gas. Okay, this one up here, I didn't ask you to identify. Oh, I erased it, but I didn't ask you to identify the gas because I don't know what weighs 3.3 grams per mole. Okay, but this one, because we could figure it out, if it's going to be easy to figure out, your instructor will have you identify what that gas is. Okay, so, oh, this should not be a B. This right here should be the next problem. It's number 5. Okay, so here is, oh, hold on a second. Okay, so here's another thing that we can do with an ideal gas law. Okay, so they've told us a sample of magnesium chlorate is heated and decomposes, producing magnesium chloride and a gas. Okay, so they told us a reaction occurred. We're going to have to do a balanced equation every single time. If a chemical reaction occurred, you will have to do a balanced equation. So magnesium chlorate, and chlorate is a -1, magnesium's a +2. So if we swap those, we need 2 chlorates. Oh, I meant to make that black. We need 2 chlorates. It decomposes. Okay, so if your instructors require this, decompositions are done on solids. That is a solid. It requires heat. The triangle above the arrow is heat. And it produces, they told us, magnesium chloride. Magnesium's the +2, chloride -1. So we swap those. Chloride gets the 2. And a gas. Well, what would that gas be? Look at what you have over here. The only thing you have besides magnesiums and chlorides is oxygen. So it has to be oxygen gas. And you know oxygen gas is O2. Okay, so this produces solids and gases. Okay, so now if we go to balance this thing, I have the 1 magnesium and 1 magnesium. I have here my 2 chlorides and 2 chlorides. Okay, here I have 6 oxygens. So I'm going to put a 3 in front of the O2, and now I have 6 oxygens. So I'm balanced. Okay, so a reaction occurred. So first we had to do a balanced equation. Okay, now that we have our balanced equation, let's look at our information. So they gave us a mass of the solid. Okay, so that's different than above. Above, we were given the mass of the gas. Okay, it produces, so I have a volume here, is collected. Oh, and look, they even told us in the problem that it was oxygen gas. Look how handy that was. Oh, and it's collected over water. So we're going to have to talk about this. I've been given, so I have a volume given. I have a temperature given. And I have a pressure given. Okay, so there's not 2 of anything. So we know, no matter what, we are using PV equals nRT. Okay, so on the side of my paper, PV NNT. Okay, so let's talk about that collected over water. I'm going to pop over to this other screen real quick. Okay, so if I have a container here, okay, and it's closed off, I have just a little hose coming in, and I am collecting gas. I'm collecting oxygen gas, okay? And I'm collecting it over water. Okay, so oxygen is coming in here. I'm collecting it over some water. Okay, at room temperature, water evaporates. So there is some water gas, water vapor in there. Okay, we want to know only the oxygen gas. We want to know the pressure of the oxygen gas. So in the next video, when I talk about other gas laws, I talk about Dalton's law of partial pressures, where we say our pressure total for this is equal to our pressure of oxygen plus our pressure of water, right? That's all the gas in there is oxygen and water. So the pressure of two of those is all of our pressure. So if I want to know my pressure of just oxygen, I subtract my pressure of water, right? Okay. So when we're collected over water, a gas collected over water, you have to subtract your pressure of water to get your pressure of just the gas you're talking about. Okay. So, oh, that wasn't what I wanted to do. So when we do that for this, okay, we look at, go to here, we look at, they will give you a table that is the vapor pressure of water at specific temperatures. Okay, and the temperature on that one was 23 degrees Celsius. So we look at our table and we find 23 degrees Celsius. And all of these, by the way, my lines are here. All of these are in millimeters of mercury. That's why I'm not converting that temperature yet. You first have to subtract off your water before you convert to ATM. Okay, so at 23 degrees Celsius, 21.1 millimeters of mercury. Okay, so 21.1. So go back to here. So I have to take my pressure, which was the 764. Let me get my pen back. So I have that pressure, the 764. So I have 764 millimeters of mercury. I have to subtract off that 21.1 because this is my pressure total. This is my pressure of water. And that total afterwards, I get 742.9. Okay. That's my pressure of just the oxygen. But now we need to be in ATM because our R value is in ATM. So we know 1 ATM is 760 millimeters of mercury. And when we do that math, we get 0.9775. And if you want to leave that, you can leave that. We're at 3 sig figs technically, because that number was 3 sig figs. Okay, and 0 decimal places when we did that subtraction, and that's 1 decimal place. So that's, oh, I lost my number. 742.9 millimeters of mercury. Okay, and so technically this is 0 decimal places. So that's just the 742. Okay, so we have the 0.9775 ATM. Our volume, oh, here, let's talk about this. We forgot to look at what we're looking for here. Let me erase some of this stuff. Okay, so we got the collected over water. Our questions are our actual yield, theoretical yield, and percent yield. Okay, so if they're asking us for an actual yield, okay, yield of gases is volume. So what I want you to recognize is this volume they gave us, that is our actual yield. Okay, so I'm going to go down here. So my actual is the 175 milliliters of oxygen. Okay, so because they're asking for the percent yield, right? Remember, percent yield is your actual over the theoretical times 100%. Okay, so they have to give us, remember, the actual is a given value and theoretical is calculated. Okay, so our actual has to be given to us. So in a gas law, if they are asking for percent yield, the volume that they give you will always be your actual. Okay, which means that volume does not go in the volume for your gas law. That doesn't go there. Okay, so continuing to look at our information, we have our sample of the solid. We're not looking at that yet. We have 175 mils of oxygen as our actual yield. We have collected over water. We subtracted off our water for our pressure. Our temperature was 23 degrees Celsius, 23, yep, just 23, plus the 273.15 gives me 300.15, but we're 0 decimal places and 2, so we're going to go with 0. Okay, so we're 300, and that has to be the 3 sig figs for the 0 decimal places, so you have to put a decimal on that to give yourself the 3 sig figs. Okay, so now I pulled all of my information except for that solid. Okay, that right there. Okay, well, we're looking for percent yield. We've been given that volume, so our theoretical yield is also going to be in milliliters. So our volume is what we're solving this gas law for. Okay, so remember earlier when I said do moles last, and that if that's all that's left, that's what you're looking for? Okay, well, I have 2 things here I don't know, which means your moles is coming from the other piece of information given to you. We want to know how many moles of O2 is what we're looking for there. If I start with the 0.615 grams of the magnesium chlorate, right? This is just our stoichiometry. We need to go from grams of one to moles of the other, so we have to cross that mole river. So first we have to get to moles, and the molar mass of magnesium chloride I got is 191.21 grams of it, magnesium chlorate, sorry, to 1 mole. Okay, so some students are tempted to stop right there because they're like, ooh, I'm at moles. But we need moles of gas. Gas laws are only good for gases. Okay, so I need to now put my stoichiometry in there and say from my balanced equation, I have 1 mole of the magnesium chlorate to my 3 moles of oxygen. Okay, those cancel, those canceled. Okay, and when I do that math, I get 0.009649 moles. Up here, I forgot to mark that, so we're limited to that sig fig, 3 sig figs up there. On this one, we're also limited to 3 sig figs. Okay, when I did my math, I did not leave all those sig figs. I had already rounded. Okay, so now we know we're using PV equals nRT, and we are isolating V, so we're moving P down to the bottom on the other side. Okay, so we know that our V is equal to nRT, make that look like an R, nRT over P. So my V is equal to my number of moles, and we got that as 0.0096. I used 5, I rounded that. And my R value, because R has a top and a bottom, I go ahead and just put it as a top and a bottom. I put my K-mole on the bottom because then I can see my units canceling. Okay, my temperature was the 300 K, and my pressure was the 0.97. I rounded that to 8. Okay, and if you look, our moles cancel, K's cancel, ATMs cancel, and you're left with a volume, which is what you're looking for. Okay, so when we do that math, I get, let me find it. I get 0.24288 liters, right? But because this percent yield is going to be my actual that they gave me in milliliters, that's why this answer has to be in milliliters. Okay, now technically we're limited to 3 sig figs on that. Okay, so we need to turn that into milliliters. So I've got 242.88 milliliters. And I rounded it when I did my math. It's 3 sig figs. So I put 243 milliliters times 100%. Those mils cancel, and you're left with just your percent. And when you do that calculation, I get 72.016. I'm limited to 3 sig figs, so 72.0% yield. Okay, so my theoretical was, let me fill that in there, it's 243 mils. Okay, so there's all of our answers, our actual yield, our theoretical yield, and our percent yield. Okay, so there's a lot going on there, but we just parse it out, okay? If you are given every single time, if you are given the mass of a solid, or basically a non-gas, okay, in a gas law problem, that is typically how you are going to get moles to then solve your gas law problem. Okay, so there was a lot going on in that problem. We had a balanced equation, we had a reaction that happened, we had to do a balanced equation. We had to subtract off the pressure of water because we were collected over water. If you are not collected over water, you do not need to worry about that. But if you're collected over water, you must subtract your pressure of water. We put all of our other stuff in there. We converted all of our units into what we needed to be in. We got our ATM. We got our K. We converted our solid over to moles of our gas, solved that gas law for the volume, our theoretical yield, and then took that actual. Because remember, if they're asking for a percent yield, whatever volume they give you in a gas law, that is your actual yield. And you are solving the gas law for the volume of your theoretical yield. Okay, a lot going on there. Okay, so this one should actually say number 6. I don't know why that says C there. Okay, so if we're looking at another thing that we can do with the ideal gas law, okay, I've been given, so here's what we can do. We can identify an unknown metal, X. Okay, so from gas law information, if you do an experiment, you can actually do an experiment and identify what the identity of a metal is. Okay, so we've been given grams of an unknown metal. Okay, so, and this is asking us, okay, so it was reacted with hydrochloric acid according to the equation below. So they've given us a balanced equation because we don't know what that metal is, so we wouldn't know what its charge is, so we wouldn't know what its formula is, so we would not know how to do a balanced equation. So if you're identifying an unknown metal, we have to give you the balanced equation. Okay, and I was given a volume. I was given a temperature. I was given a pressure. I was not given 2 of anything. So it's probably a pretty good chance that we're using PV equals nRT. So see, as I read my problem, I kind of parse it out. Oh, that's a T, not an R. We know what R is. Okay, calculate the molar mass of the metal. There's our question. So we're looking for how many grams of X, our metal, over moles of X, our metal. Right? And I know X is the metal because they said our metal reacts with hydrochloric acid. So I know that X is my metal because in the reaction, that's what's reacting with hydrochloric acid. Okay, so they gave us our grams of metal. Okay. So we are not using that to calculate moles of gas because we need it for the calculation of the molar mass of the metal. Up here, they were not asking for the molar mass of the metal, so the metal was used to get to our moles. But as I always say, if you don't know what to do with the gas law, just start putting your information in and see what you need to solve for. So I have 765 millimeters of mercury. I was not collected over water, so I don't need to subtract water. I'm just going to convert that into ATM. And when I get that, I get 1.0065 You could leave it like that. I rounded it to 1.01 ATM. Okay, but if you leave it like that, make sure you mark that that's a 3 sig fig number. Okay, my volume was 35.00 mils, but I have to be in liters. So I'm going to convert that right there. That 1 liter is 1,000 milliliters. So I have 0.03500 liters. And we keep those zeros, right? Because they're significant because there's a decimal in that number. My temperature is 24 degrees, 24.0 plus the 273.15. I get 297.15. We have 1 decimal place here, 2 here, so we would have 1 decimal place in our number. So that's 297.2. Okay, you can leave it like this, but put a line above your 1 to remind yourself it's 4 sig figs. So you see, the one thing we don't know is our number of moles. So we must be solving this gas law for a number of moles. But we do know, if we need to know our moles of our metal, we can get there through the stoichiometry of moles of metal to moles of our gas, right? So anytime they give you gas law information and they're asking for the molar mass of a metal, then it's always we're solving our gas law for moles of gas, and then we'll convert that to moles of metal. Okay, so right here is we're solving PV equals nRT. We're isolating N, so RT is going to come down to the other side. So I know my N equals RT. Oh, sorry. N equals PV over RT. So it equals my 1.01 ATM over times my volume, 0.03500 over my R, 0.08206 ATM liters over kmol. My temperature was the 297.2 K. And if we look at our units, ATM cancels, liters cancel, Ks cancel, moles on the bottom of a fraction, so it comes to the top, and we're left with moles. That's what we want. So when we do that calculation, I get, I'm going to leave myself enough room on this problem. Okay, I'm going to come down here. So I get my N equals 0.001444946 moles, but that's moles of my hydrogen gas. That is not moles of my X. So I have to do my stoichiometry to say for my balanced equation, we have 2 moles of X to 3 moles of H2. So 3 moles of H2 on the bottom and 2 moles of X on the top. And if I do that math, I get, where is that? Oh, 9.66 times 10 to the negative 4 moles of X. Okay, so now for our final problem that we were looking for, how many grams of X to how many moles of X. My grams of X they gave us was the 0.0251 grams right here. My moles I calculated to be 9.66 times 10 to the negative 4. Okay, and when I do that math, I get, I don't seem to have my final answer here. Okay, let me just calculate that real quick. Okay, so 0.001449 times 2 divided by 3. Oh, that is my final answer. Hold on. Okay, that's right. Oh, there we are. I got it. Okay, 26.0. So when I do that math, I get 26.0 grams of X per mole of X. Okay. And hold on, let me look on my periodic table here. Okay, so now if it says, oh yes, it does. Okay, it does say identify that metal. Okay, so now we know that our molar mass of our metal is, and now I lost where I wrote that. Oh, it's up here. So it's 26.0 grams per mole. So we go to our periodic table and we look for the chemical that is closest to 26 grams per mole. Remember, we did a lot of rounding on that, so it's going to be close but not exact. So over here, okay, so magnesium is 24, aluminum is 26.98, and we're at 26. So it looks like aluminum is the closest one. Okay, and remember, it's an experiment, so there's always error involved. We're not going to get the exact molar mass of the metal, but it's closest to aluminum. So we would say that that metal is aluminum. Hmm. So this one was a little bit involved as well, but this one was just you were given one piece at one pressure, one temperature, one volume. So you put it all down, you say, oh, moles is what I'm looking for. And then recognizing that we want the molar mass of the metal means that we want the grams of the metal over the moles of the metal, and we can always get to moles of X through moles of my hydrogen, moles of my gas. Okay, so anytime they're looking for molar mass of a metal, okay, you're solving your gas law for moles of gas, converting it to moles of metal, and then dividing your grams by your moles. Okay, so another thing that we can do with this, and this should actually say number 7, I don't know. Okay. So, by the way, if you are in allied health chemistry, you will probably not do calculations like these following two. You might, it depends on your instructor. If you're in general chemistry, you absolutely will. Okay. So this is now asking for the molar mass of a gas. Okay, so we had the molar mass of the gas earlier, but they gave us the mass of the gas. In this one, we do not have the mass of the gas. We have a pressure, we have a temperature, and we have a density, but we don't have a mass of the gas. Okay, so anytime they're asking for molar mass of a gas and you're given density, your equation is, and they use this weird looking M, that's molar mass, is equal to density times RT over P. Okay, so I remember a student years ago said to me that that is mud equals dirt over P, because if you put dirt over P, it's going to turn all muddy. So you can remember that molar mass of a gas is mud is dirt over P. Okay, so we're just going to put our density is 3.170 grams per liter. Remember, density of gases is in liters because we don't look at it in milliliters. I don't think we talked about that. Density of a liquid is always in grams per milliliter. A solid is grams per cubic centimeter. And a gas is always grams per liter, right? Because we look at gases in terms of liters, not milliliters. Okay, so 3.170 grams per liter. And we say times our R. I'm just going to do this. So our R is 0.08206 ATM liters over K mole on the bottom. My temperature is the 350 K. If that were in Celsius, we would have to convert it to Kelvin. So 350.0 K. And my P on the bottom, so my pressure, if that were in millimeters of mercury, we would have to convert it to ATM because R is in here. Remember, when R is there, you have to be in liters and ATM. Okay, so my pressure was the 1.087 ATM. And if you look at your units, your liters cancel, your ATMs cancel, your Ks cancel, and you are left at grams per mole, which is what molar mass is, right? Molar mass is how many grams per mole. Okay, so now we just do that calculation. We get our grams per mole. I get 83.75 grams per mole. And if we look here, I've got 4 sig figs, 4 sig figs, and 4. So I'm going to go with 4 sig figs. So 83.75. I think what I actually got, hold on, was 83.7585. So I did not round that correctly. So 83.7585. I want 4 sig figs. 8 is going to round that up. So it's 83.76 grams per mole. So now that next question asks me if the gas has only one atom, it's only one atom, it's not a diatomic, okay, it's only one atom. What is the likely identity of this gas? So we're looking at 83.7 grams per mole. So we go to our periodic table and we find what is closest to 83.7576 grams per mole. Okay, so go over here, down into the 80s. Okay, so I have 83.8. Well, that's pretty close because if I rounded this to 3 sig figs, that would be 83.8, right? Let's just go to the next one. The next one is 85. So yeah, it's got to be krypton. And besides that, the next one is not even a gas. It's a metal, right? So it has to be krypton. Okay, so we are going to identify that metal as krypton. Or that gas, sorry, that gas as krypton. Okay, and this is, I believe, our last problem. Should be number 8. Okay, it's now asking for the density. Okay, so the only information we know on gases, the only equation we have on gases that includes density is that right there. Okay, so if my molar mass equals dirt over P, if I rearrange this to isolate D, my RT goes to the bottom on the other side, and my P goes to the top on the other side. So my density is equal to my pressure times my molar mass over my RT. Okay, so I have the pressure. Oh, okay, so because R is in here, right, 0.08206 ATM liters kmol, we have to be in ATM for our pressure and K for that temperature, right? So over here, I'm going to say my pressure is 3230 torr. And remember, torr is the same thing as millimeters of mercury. So 1 ATM is 760 torr, just like it's 760 millimeters of mercury. And when I do that conversion, I get 4.25 ATM. And our temperature needs to be in Kelvin. So I have negative 25.0 plus 273.15. And when I do that math, I get 248.15. And I've got 1 decimal place, 2 decimal places. And remember the decimal places because we're adding. That's why I'm always looking at decimal places on those temperatures. It's because addition, subtraction, your sig figs is your least number of decimal places. So I'm going to go with 1 decimal place in my answer. So that's going to be 248.2 because the 5 rounds that up. So 248.2 K. Okay, so my pressure is 4.25 ATM. My molar mass, oh, well, it's nitrogen. So we have to go calculate our molar mass. So when they're asking for the density of the gas, they're going to tell you what the gas is. You have to go get your molar mass off the periodic table. Up here, we didn't know what the gas was. we were calculating the molar mass to find it. Here we know the gas, so our molar mass is nitrogen times 2 is 14.01 plus 14.01, right? So it's 28.02. So my molar mass, don't know what keeps going on with that. It's 28.02 grams in 1 mole on the bottom, right? I need some space here. And my R, 0.08206. Oh, I'm out of room. Let me do something here. Give myself a little space. So 0.08206 ATM liters over kmol. And my temperature on the bottom there, we decided was 248.2. If you look at all of this, your ATMs cancel, your Ks cancel, your ATM Ks, your liters cancel somewhere. Oh, no, we're looking for density. Density is grams per liter. Sorry about that. I don't know where my mole canceled. Hold on just a second here. There it is. I lost my mole. This 28.02 is grams per mole. So there is a mole on the bottom down here. And that mole on the bottom of that fraction cancels that mole. And in the end, we're left with grams per liter, which is what we're looking for. That is what density is. Okay, and if you do all of that math, we get 5.85 grams per liter. Okay. So if they give you a density of a gas, you're going to use it using this calculation right here, that equation. If they give you the molar mass, if they give you the density, you're going to use it to get to molar mass. If they ask for the density, you're using the same equation. You just rearrange it to solve for density. Okay, so that is all I can think of at this moment that you can do with the ideal gas law. There's a lot of different things that you can do with it. Okay, so yeah, I think that's all I have to say about the ideal gas law today. Have a great day. It turns out I have 2 more things to talk about with the ideal gas law. Sorry I tricked you and made you think that the video was over. So just a few more minutes. There are 2 other things we need to talk about, and that is when you are at, oh, that's crazy, when you are at constant temperature and pressure. And we talked about, no, we didn't talk about that. I'll talk about in my next video. Never mind what I was just saying. So at constant temperature and pressure in a balanced equation, you can consider the moles as liters. Okay, it has to do with some of the combined gas laws, Avogadro's gas law and Gay-Lussac's gas law, which I'll talk about in the next video about the combined gas laws. But a relationship between those and numbers of molecules and etc. If we are at constant temperature and pressure, we can just use our moles as liters from our balanced equation. So let me give you an example of that. So what if I said that you had potassium chlorate, solid, decomposing in heat into potassium chloride and oxygen gas. Okay, if I balance this, I need 3 of those, 2 of those, 2 of those. Okay, so what if I say how many liters of oxygen when 4.4 grams of potassium chlorate reacts at constant temperature and pressure. Okay, so my question is how many liters of the oxygen gas, and I'm going to start with the only number I know, my 4.4 grams of potassium chlorate. Okay. So we could do a gas law on, oh no, we cannot do a gas law on this because we're at constant temperature and pressure. So anytime you're at constant temperature and pressure and they're asking about that volume of a gas, you're just going to use stoichiometry. Okay, so first we need to, because if we get to moles of O2, we can just consider that to be liters of O2. Okay, so first I need to get to moles of potassium chlorate, and I have that it weighs 122.55 grams of potassium chlorate in 1 mole of potassium chlorate. Okay, so right here, I can say that I know up here, because we're at constant temperature and pressure. Ooh, I am circling the wrong things here. Because we're at constant temperature and pressure, we can say that we know that the 2 moles of potassium chlorate is equal to 3 liters of oxygen gas. Because we are at constant temperature and pressure, we can call this moles liters. Okay. And then if I just calculate that, let me calculate that real quick. Oh, I hit something wrong on my calculator. And I get 0.05385. I'm going to go with 2 sig figs because of the 4.4. So 0.54 liters of O2. Okay, so if you're at constant temperature and pressure, and they're asking about liters of a gas, you just use your stoichiometry in your balanced equation and call that liters of gas. Your moles is your liters. Okay, the other thing is STP, standard temperature and pressure. Okay, and your standard temperature is 0 degrees Celsius, and your standard pressure is 1 atm. Okay, this is also 273.15 K. Okay, and when you're at standard temperature and pressure, and only at standard temperature and pressure, there is always 22.4 liters of any gas in 1 mole of that gas. Okay, so we can use that in stoichiometry and save us from doing a gas law. Okay, so what if I said, using the same problem above, let's go ahead and go with the potassium chlorate, decomposing into potassium chloride and oxygen gas. Okay, so what if I again start with, if I say how many liters of oxygen gas at STP if, and I'll just go ahead and use the same information, if 4.4 grams of potassium chlorate reacted. Okay, so I want to know how many liters. Since we are at STP, I always off to the side write my 22.4 moles over 1 liter, and the gas we're talking about is oxygen. Okay, so I'm going to use, I see this, once I get to moles of oxygen, I can use that to get to liters rather than having to do a gas law. Okay, so I'm going to start with my 4.4 grams of the potassium chlorate. Okay, and same molar mass, 122.55 grams of it and 1 mole of it. But we are talking about oxygen gas, so we want to know oxygen gas, so we're going to use our mole ratio. But there's 2 moles of the potassium chlorate to the 3 moles of oxygen. Now that I'm at moles, I can use my conversion factor to get over to liters. That 1 mole of, oh, sorry, yep. Oh, I have this totally backwards. Sorry about that, you guys. I have my units wrong. Whew, 22.4 liters in 1 mole. Sorry about that. That's 22.4 liters per mole. Okay, so in my 1 mole of O2, I have 22.4 liters of O2, and I am where I want to be. Okay, so if I do that math real quick. Oh, wait, I did that math already here. Oh, no, I did not. Yes, I did. Okay, so I get 1.206, and we're limited to 2 sig figs, so 1.2 liters of O2. Okay, you could have done that with a gas law, saying that your P is equal to standard pressure, which is 1.00 atm. Your volume is what you're looking for. Your N, you're going to get from your okay, and we're going to do all of that same math right up until we get to moles. Okay, and now I know my 3 moles of O2 to 2 moles of KClO3. Okay, and that'll get me my moles of O2. Okay, and then my temperature is standard temperature, which is 273.15 K. Okay, so let me get those moles calculated. And I get 0.05385. I've got 2 sig figs there, so 0.054 moles. Okay, so now I can solve my gas law. PV equals nRT. If we're isolating the V, we're moving P down to the other side on the bottom. So we know V equals nRT over P. So my moles times my R times my temperature times my pressure. Okay, and if we do all of that math, I get 1.20715. And at 2 sig figs, we're at 1.2 liters, which is exactly the same value that we got up here. Okay, so you could do a gas law on that when you're at standard temperature and pressure and plug in your standard pressure and your standard temperature, use your mass of your solid to get over to moles. But you see, I had to do this much of this calculation anyway, right here. So if you just remember 22.4 liters per mole at standard temperature and pressure, it saves you from having to do that entire gas law. Okay, so that is all I have to say about ideal gas laws. So have a great day.